So let's just show that. So Rx of tau is equal to 1 over Ts sinc tau over Ts. So if tau is a multiple of the sampling frequency, then Rx of kTs for integer k is equal to, well, firstly, it's equal to 1 over Ts sinc kTs over Ts, which is sinc k. So this is equal to 1 over Ts sinc of k, which is equal to, if k is 0, what's sinc k if k is 0? Anybody know? Yeah. So sinc looks like this. And 0, what is it? So you can't, unfortunately, you can't see from the equation the limit as t goes to 0. Does anybody remember what this amplitude is? It's just 1. So this is 1 times Ts, which is 1 over Ts. K equals 0. How about at integers? So now we can see from this formula, sine of pi times an integer is what? So sine of pi times an integer is always 0. Sine looks like this. So that's pi, 2 pi, 3 pi, and so on. So that's pi, that's an integer, that's 0. This is positive, so it's 0 if k is not equal to 0. So in other words, if I take 2 samples, W of k and W of j, what's the correlation? Well, the expected value of W of k times W of j, these are just samples of the random process, or the random process W, excuse me, that should be W. That's the expected value W kTs times W jTs which is equal to, so by definition, this is all I have to pay attention to is the difference between these. That's equal to the autocorrelation for kTs minus jTs, which is equal to our W k minus j Ts. So if k and j are both integers, as they are up here, then this is an integer multiple of Ts, and this is equal to 0 if k is not equal to j, and 1 over Ts if k is equal to j. But this is the important part. What this means is that if these samples are different, then this is equal to 0. And if they're 0, then that means these are independent. Okay. So coming back to the noise, y of k is equal to ask plus wk. I think I called this n of k at the beginning of the class. We needed to know 3 things. We needed to know mean, that's 0. We needed to know variance, that is N0 over 2TS. And we needed to know autocorrelation. That is 0. So expected value of WK, WJ equals 0 if K not equal to J. So therefore, samples of the noise, different samples of the noise are independent. Okay, now we have enough mathematical machinery to be able to say what happens when the noise random process is passed through the detection filter. Any questions up to this point? So here's where we are. We came through A to D with WK. And now we're going to go through the detection filter. In fact, I'm going to say not just WK. WK is only a component here. We have Y of K, which is ASK plus WK. A doesn't really matter. So without any significant loss of generality, I'm just going to say A is 1. So this is S of K plus WK. Okay, so we have Y of K involved with H of K. That's what's up the output here. This is now the notation I used for the filter outputs was 5. I think it was 5K. I'll try to make sure I'm using consistent notation here. Okay, so Y of K involved with H of K is equal to S of K plus W of K involved with H of K. So convolution distributes over addition. So this is equal to S of K involves with H of K plus W of K involved with H of K. So what I'm going to do now is I'm going to return to the example we had last time. So the example I had last time was that S0 of K was this, plus 1 for NB samples, and S1 of K was this, minus 1. And I said H of K I think I said H of K is equal to, I think I said it's H of K is equal to S0 of K shifted over by 1 or something like that. But either way, my argument was that oh, that's right. I said H of K is equal to S0 of K. In any case, it doesn't make any significant difference if that's shifted over by 1 or